Okay, the last video I asked you to do this task on your own. If you haven't done it, I would ask you to do it before you see me do it here. So the first is construct a general parallelogram in Euclidean geometry using the standard parallel line tools. Try this yourself if you haven't done it yet, and then you're going to see me do it here. Press pause. Okay, you're back. Let's actually just go to open a new window here. Just go to GeoGebra's main site, go to Classic. This is going to be done in a basic geometry setting. So in this case, we can start with 3 free points and make line segments. I'm just going to use the line segment tool. So there's A, B, and C. Now we want it to be a parallelogram. So there's exactly one parallel line through A parallel to BC. Whoops, try that again. Exactly one parallel line through A parallel to BC. And there's exactly one line through C parallel to AB. And you can see no matter what happens, there will be exactly one intersection point right there. And so I'm going to go ahead and finish out the parallelogram like that. We can hide these lines here. And now we have a general parallelogram where A, B, and C are free to move anywhere we want, but opposite sides stay parallel. Okay, so these sides here, let's make them red, are parallel, and these sides here, let's make them blue, they're also parallel. All right, so then what's the next thing I asked you to do? I said measure all the angles. Okay, so let's do that next and see if we can figure out what's happening. So measure the angles. Okay, here's our angle measure tool. There we go. Here we go. I'm measuring in radians. That's my default, but you could go measure them in degrees if you want. Let's actually make sure that these always stay. So a couple things. We just need to, I'll put the value. We don't need the name. Let's always make it between 0 and 180 degrees. And let's just go in general to measure them in degrees, say for this purposes of this one here. Do you notice anything about the numbers here? Look at that. That one and that one seem to be the same number, and that one and that one seem to have the same measure. So let's take these two and maybe get them the same color. So it looks like we have some congruent angles. Well, this is just one example. Let's see if it changes. These are the same. Those are the same. How about if we do that? 55.9. Yep, that's the same. That's the same. Looks like it's working, doesn't it? Okay, how can we prove this? And I said you could prove it without making any extra drawings on here. Well, the thing to remember is if these two lines are parallel, which they are, these two angles must be supplementary. But these two lines are parallel, AB and DC, so the angle at D and A must be supplementary. Well, the angle at A is supplementary with B, angle at B, and it's also supplementary with the angle at D. That makes the angles B and D congruent, same measure. And a similar argument gets C and A congruent. So the fact that we have the two sides there, we were using the C property that interior angles on the same side of the transversal must be supplementary if and only if the sides are parallel. So we get that. And so we get that result. Now, by the way, the order we're doing that doesn't work in hyperbolic geometry, so this would not necessarily be true in hyperbolic geometry. Okay, well, that's cool. We can show that we have some congruent angles. and we didn't have to even draw anything there. The next thing I ask you to do is draw in one of the diagonals. Let's say we draw this one in. It doesn't really matter which one. Or does it matter? Let's find out. Now, what does it look like on these two triangles right here? Well, it looks like they might be congruent. Okay. Well, we have a pair of congruent angles there that we've already proved. But if you look, because of these are congruent, we have a z property. You see the z? So that means that this angle here and the angles here, again, we want to make sure these angles here and here, let's see. Got that one and this one. Let's see, between 0 and 180 degrees. All right, so now let's look at what we've got. What do we get for that angle? There it's 18 degrees, about the same there. Yeah, it is the same. So Z property says those angles are the same. So now we have angle, angle. And of course the side BD is congruent to the side DB. It's the same side, same length. So that's side, it's angle, angle, side. Or if we do the Z property again, that we're using the fact that these are congruent, then your Z is going sideways like that. Then we get the angle there at D, that's BDC, is congruent to angle ABD. And so we get that these two triangles are congruent to each other. But they're congruent to each other with a reflection, not a reflection like they were with the what was it? With a kite. They're congruent a different way. Can you see it? How are these? What transformation maps this side to that? Well, it's going to send D to B and B to D, and it's going to send C to A. Well, that's a rotation. No, yeah, it's a rotation. So let's see if we can illustrate that. So let's rotate C about point E, and by what angle? Pi radians or 180 degrees. Turns out if it's 180 degrees, it doesn't matter whether it's clockwise or counterclockwise. And look where C prime is. It's right on top of A. So no matter where we move this guy, it's going to land right on top. So that says that and of course we do the same thing. D is going to rotate to B, B is going to rotate to D. And so the whole triangle gets rotated so that we have a rotational symmetry here. And what is E is the midpoint of that diagonal. Well, what if we do the other diagonal? Does it make any difference? Which one we started with? Okay, well, now look at, let's just get rid of that guy. Look at those two triangles. Well, they're congruent as well. Same argument as before. This time the angle, this time it's the angles up here and here. That's DAC is congruent to BCA by the Z that way and the Z going this way. Angle ACD is congruent to angle ACDC CAB. And so, and then this is congruent to itself. So once again, we get side, our angle side angle in this case, or angle angle side, depending on how we do it. We're going to get these two triangles congruent. Once again, we can see this. We rotate this triangle around the midpoint of this side. We get the same thing. Well, it turns out that the diagonals actually meet each other at the midpoint. So the midpoint there is the midpoint here. Okay. And so that's interesting. So it looks like the diagonals bisect each other. How can we prove that? Oh, by the way, I'm getting ahead of myself. What about what else did I ask you to do? I asked you to measure all the sides just say value will show their sides. I didn't necessarily need to show the label on that guy. Okay, and so what do you notice about the opposite sides? Not only are they parallel, look what else happens. They're actually congruent to each other. So how could I prove that? Well, let's get rid of that diagonal for the moment. Okay, so what do we have? Well, we use the fact that we have these two congruent triangles. Remember, we just proved that. And what do we know? Corresponding parts of congruent triangles are congruent. That's the definition of congruent triangles. So these two sides are congruent because they correspond, and these two sides are congruent because they correspond. Okay. What about the converse of that? Well, what if you have both sides are congruent here, both pair of opposite sides? So if the two reds are congruent and the two blues are congruent, both pair of opposite sides, of course the diagonal is congruent to itself. The two triangles are congruent, this time by what? The side-side-side triangle congruence theorem, SSS. So that would make these two congruent, which means angle D, whatever this is A, I think, DAC. Let's go ahead and show the label there, but we just want to show its name. Angle DAC is congruent to angle BCA because those are corresponding angles from two congruent triangles. And then what happens? Well, that makes a Z right here, and we have a pair of alternate interior angles cut by the transversal, which contains the diagonal there. And so that makes the two sides parallel for the Z property. In a similar way, we get a pair of corresponding alternate interior angles that are congruent, corresponding between the two triangles, and we get a Z property with the angle right here, BAC congruent to DCA, and so that makes the two triangles are congruent. So we got the angles congruent, therefore we get the sides parallel. Again, using the Z property for Euclidean geometry. Okay, now let's go back to here. If we look at the diagonals here, what do we have? Well, it turns out this triangle right here and this one over here, that is triangle ABE, is congruent to triangle, now we got to get the right order, CDE. Well, you've got a pair of vertical angles right here that are congruent. We've already proved that we have these sides congruent. You need to do that first. So once you have that, then we've got all the angles we need. Either we get the pair from vertical angles or we get the other two from the Z property. And so we either angle, angle side, or angle side angle. You get those two triangles are congruent to each other. And the same kind of proof, same steps show that these two triangles are congruent. Well, among other things, it says that this side is congruent to this one because they're corresponding sides. Means E is the midpoint of AC, and similarly, side BE is congruent to side DE, so E is the midpoint of that side. So we see that the diagonals bisect each other. Notice that they're clearly not the same lengths. In fact, it's actually kind of deceiving. What's this? If I do a circle with a center and radius, and the radius is the distance from A to C, look how short it is. How much shorter that side is than this side. It would only go, if you were to move this one over here, it would only go that far out. So definitely you do not get congruent diagonals, at least not usually. And so we get that. So what do we know about opposite angles? They're congruent. The other opposite angles are congruent. If you take consecutive pair, they're going to be supplementary. We've got opposite sides congruent. We've got two triangles when you make a diagonal are congruent. The other two triangles when you make the other diagonal with the sides are congruent. The four little triangles have two congruent pairs. The diagonals bisect each other. So we have lots of cool properties for quadrilaterals. And the key really was this fact that triangle ABC was congruent to triangle CDA. So these triangles are congruent to each other with a rotation of 180 degrees about the midpoint of one of the diagonals, or midpoint of both the diagonals. It's the same point. And it turns out that this class of quadrilaterals, if you phrase it that way, does exist in hyperbolic, spherical, and Euclidean geometries. And that class in those three geometries has all pretty much the same properties. It flows from uh, that congruent triangle relationship. So if ABC is congruent to CDA, that's the given. Then it turns out the other pair of triangles is congruent too, that ABD is congruent to CDB. Also, the four literal triangles where x is the intersection of the diagonals are congruent, where you have AXB is congruent to CXD and AXD is congruent to CXB. That's the little triangles that we were looking at. It has rotational symmetry about the intersection of the diagonals by rotation of pi radians. Both pairs of opposite sides are congruent. Both pairs of opposite angles are congruent, and the diagonals bisect each other. So that happens in all three of these geometries if you get these triangles congruent. Now, in hyperbolic and Euclidean geometry, both pairs of opposite sides have to be parallel, so it's a parallelogram. But of course, parallelograms don't exist in spherical geometry. Now, in hyperbolic geometry, parallelograms are a larger class than this. Just because it has a parallelogram doesn't mean these triangles are congruent in hyperbolic geometry. But in Euclidean geometry, the class of quadrilaterals with this ABC triangle congruent to triangle CDA is exactly the same as the class of parallelograms. Another thing that you have is that any pair of consecutive angles are supplementary in Euclidean geometry. Doesn't happen necessarily in the other geometries. Okay, so again, here's a diagram. So once again, in hyperbolic geometry, the class of quadrilaterals ABCD with triangle ABC congruent to triangle CDA is a proper subset of the class of parallelograms. In Euclidean geometry, the class of quadrilaterals ABCD with triangle ABC congruent to triangle CDA is exactly the same as the class of parallelograms. In spherical geometry, there are no parallelograms because there are no parallel lines, but a class of quadrilaterals ABCD with triangle ABC congruent to triangle CDA does exist in spherical geometry. So next we want to do a couple of things. A couple of them we've actually already done. We want to prove the properties listed for the indicated geometries, and I kind of talked you through that proof already. We also want to consider the converses of some of these properties. We looked at one. We showed that if a quadrilateral is a parallelogram, at least in Euclidean geometry, then it has to have both pair of opposite sides congruent. So both pair of opposite sides parallel implies both pair of opposite sides congruent. What about the converse? Well, the converse is if you have a quadrilateral with both pair of opposite sides congruent, do both pair of opposite sides have to be parallel? Okay, or another way of thinking about it, what would be some minimal set of conditions for us to determine if a diagonal divides the quadrilateral into two triangles which are congruent to each other with a rotation? So in the proof below, we're going to have a little table, and we're going to look at different converses. These are going to make use of the Z and C properties as well as the triangle congruence theorems. All parts of the following proof work in both directions in Euclidean geometry. However, some parts only work in one direction and not the other, or don't work at all in hyperbolic and or spherical geometry. And the details are tracked in the table and in the proof. In general, one considers a conditional if-then statement, such as nearly all propositions. One should also consider the converse. In general, if a statement if P then Q is true, then the converse if Q then P may or may not be true. It depends on the statement. But a good mathematician is always looking at every proposition and seeing what it says when it is restricted to special cases, asking if it can be extended to more general case, seeing what happens if part of the hypothesis is eliminated or modified, and seeing if the converse is true. So I think I'll do this proof on its own in the next video.